Today we're going to learn about solving nonlinear systems, such as a quadratic and a linear function, or two quadratic functions. So what can the solutions look like? When the graphs of the equations in a system are a line and a parabola, the graphs can intersect in 0, 1, or 2 points. So the system can have 0, 1, or 2 solutions, as shown. When the graphs of the equations in a system are a parabola that opens up and a parabola that opens down, the graphs can intersect in 0, 1, or 2 points. So the system can have 0, 1, or 2 solutions as shown. For number 1, we're going to solve this system by graphing. We have a quadratic function in standard form and a linear function. For standard form, I'll determine a, b, and c, and then find the vertex using negative b over 2a for the x part. To find k, we'll plug in 1 for the x's in the quadratic equation. Graph the vertex and remaining points of the parabola. Your line has a y-intercept of 0, -1, and a slope of -2 over 1. Graph the linear function. It looks like our line touches the parabola at 1 point. So we have one solution at 0, -1, because that is our point of intersection. For number 2, let's solve the system by substitution. That means we'll isolate either x or y in one of the equations and substitute that expression into the other equation. I'm going to take equation 2 and isolate y. Now plug this expression in for y in equation 1. Solve for x. Here we have a quadratic equation. The first thing I'm going to try is to bring everything to one side and try factoring. We need two numbers whose product is -3 and sum is +2. 3 and 1, where the 1 is negative and the 3 is positive. Now use zero product property to solve. It looks like we have two x values, so go ahead and plug these into equation 2 in order to find the corresponding y values. That makes one of our solutions the point -3, 7. Now solve for y when x is equal to 1. The y value that corresponds to 1 is 3, which would be our other solution. Each of these solutions will make both equations true, so you can always check by plugging in x and y to make sure your solutions are correct. For number 3, we're going to solve the system by elimination. Immediately, I notice the coefficients of y are +1 and -1, so I can immediately start adding. Now let's solve this quadratic equation. First, we're going to make it equal to 0 and see if we can factor it. There's no way to factor it. Then I look for what is b. b is not 0, so I can't use square root property of equality. A is not 1, so it's not a great candidate for completing the square. So let's use the quadratic formula. We have it already in standard form. A is 3, b is -3, and c is 2. The opposite of b, plus or minus, the square root of b squared minus 4ac. All over 2a. Now let's simplify. Now I could simplify this, right? I could write it as 3 plus or minus I root 15 over 6, but if you remember, we're solving a system, and the solution is a point or multiple points. This solution is imaginary, which means it's not on the real number system, and because of that I, we have no real solution. For number 4, x squared plus y squared equals 4. This is not a quadratic equation because y is also being squared. Do you remember which parent equation this is? X squared plus y squared equals r squared is a circle. So in this case, r squared would be 4, so your radius is 2. A circle with radius 2 centered at the origin. And here we have the line y equals x plus 4. Go ahead and substitute x plus 4 into y in our first equation to solve by substitution. Remember that x plus 4 squared is x plus 4 times x plus 4, and you'll need to use double distribute or box method to simplify this. And notice that this quadratic equation has a GCF. 2 goes into each of these terms. So go ahead and factor out the 2 and then divide both sides by 2. Now go ahead and see if you can factor this quadratic equation. Turns out we can't factor it, but a is 1 and b is even, so this is a really good opportunity to complete the square. And if you notice, we have another imaginary answer. So that means that this one does not have a real solution. If you notice in the graph, our line does not intersect this circle. If we did get real x values as solutions, we would plug them back in to this equation in order to get the corresponding y's for our solutions. For number 5, you don't even have to find the y values, but we want to solve the equation for x, so begin by putting it in standard form, making it equal to 0. I don't want my x squared term to be negative, otherwise I'll have to factor out a negative if factoring is involved. So let's add the x squared to the left side. You could try factoring this, but it's not factorable. So I'm going to move on to quadratic formula since a is not equal to 1 and b is not equal to 0. No imaginary numbers this time, so we do have a solution, and we didn't have to plug in to find any y's. So our solutions are -3 plus root 41 over 8 and -3 minus root 41 over 8.